something that has historically been a challenge for my students to do is to differentiate or tell the difference between Mauna Loa and Mount Fuji because they're both obviously volcanic places. And so what you should be using this video for is to check your work on the comparison chart, really the contrast chart between the two of them. And the hardest part to do, I'm sure, was the sketch because you really have to think through the whole plate tectonic story and reread your travel log to be like, how would I actually draw that? And so I asked you to draw both above ground and underground. So let me show you how I've approached this. I want you to check your work like this. For Mauna Loa, which was on the left-hand side of your chart, do you have a wide volcanic mountain with a gentle slope? And Mount Fuji, do you have the opposite? Do you have a much steeper slope for Mount Fuji? That's what you should have. Now, if you have anything coming out at Mauna Loa, which is a good idea, it should be lava. At Mount Fuji, it should be an ash column and little other pyroclastic materials maybe littering the sides like volcanic bombs and lapilli. Now, what about underground in your sketch? So the most important thing to me, I think, two things, are the number of plates and the arrows. So notice this. In Hawaii, there's just one plate, and I know there's 4 arrows in that diagram, but it's just trying to show motion in that one direction. So one plate, finish this thought in your mind, traveling over a something, traveling over a hot spot. So you must have a hot spot underneath, rising up, up, up. The hot spot doesn't move, the one plate does, and that's how we get an island chain. We can tell that this hot spot hasn't always been as active as it is because we get breaks between the islands and different size islands. One plate in Hawaii moving over a hot spot that stays. Now, Japan is a totally different situation. Finish my thought. Not one plate, but 2. Very good. And so now you have 2 arrows, and those should be pushing toward each other. They should be converging. Remember, this is a continental oceanic convergent. It doesn't matter which side you put which on, but the oceanic side must be performing the sinking. And then this should be labeled, this is actually a little high on here. It's really the sinking action that is called the subduction zone. So just like you should have a hot spot labeled on Hawaii, you should have a subduction zone that's labeled on Japan. Sketching these places is a big part of your non-retakeable plate tectonics test. Okay, so you have the sinking oceanic crust, and then you, of course, on top have that volcanic mountain. Now be careful, don't have your continental crust sinking. The minerals, the silicate minerals in continental crust are not as dense. It's the oceanic that should be sinking and making a magma pocket at the subduction zone. Okay, so that was your sketch. Now, this part is more simple. What type of eruption? Mauna Loa, you should have the word non-explosive. There's no other right answer. Mount Fuji, explosive. So this is actually a picture of Mount Pinatubo in the Philippines that erupted in 1991. But scientists know that in the 1700s, Mount Fuji did the same thing. Now, you might be like this, Mrs. Fickus, in that picture, I think right there, that is ash. No. That's actually steam. That's water vapor coming out. Notice that lava is what dominates in non-explosive eruptions like Mauna Loa. Okay, so speaking of lava coming out, what dominates in Mauna Loa is lava. Do you notice this from similar to the work Mrs. Shields and I did? And then Mount Fuji is different. The term for it is pyroclastic materials. You could have put rock chunks. You certainly could have put ash, lapilli, or volcanic bombs. Those are all good answers for what comes out. Now we get into the reason why. How's the viscosity? So think of it like this. Where does the magma resist flow? And the answer to that is Japan. That's why you have this pressure building. And so the viscosity at Mauna Loa is low. That's why you have the wide shield volcano. The viscosity at Mount Fuji is high. And the reason is because of the silica differences. Low silica in the magma, not much tight-fitting silica, runny lava flows. Mount Fuji, there is a lot of tight-fitting silica clogging the vent of the volcano like the black stopper. Now, the last one was more of a guess. I know that this hasn't been a big part of our lab work, so you may have to fix this one up. But in general, non-explosive eruptions are lower in gas content. Explosive eruptions are higher. I actually think about my cans of Coke Zero. If I accidentally shake it or one falls out of the carton, I certainly wait to open it, because as gases get rumbled around, that adds pressure and will lead to an explosive eruption, or help it to be an explosive eruption. So use this presentation and the work you've done to help you contrast between Mauna Loa in Hawaii and Mount Fuji in Japan.